Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Machine Learning Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You are building a linear regression model on BigQuery ML to predict a customer's likelihood of purchasing your company's products. Your model uses a city name variable as a key predictive component. In order to train and serve the model, your data must be organized in columns. You want to prepare your data using the least amount of coding while maintaining the predictable variables. What should you do? The options are: Option A, use TensorFlow to create a categorical variable with a vocabulary list. Create the vocabulary file and upload it as part of your model to BigQuery ML. Option B, create a new view with BigQuery that does not include a column with city information. Option C, use Cloud Data Fusion to assign each city to a region labeled as 1, 2, 3, 4, or 5, and then use that number to represent the city in the model. Option D, use Dataprep to transform the state column using a one-hot encoding method, and make each city a column with binary values.
To arrive at the correct answer, we focus on the keywords: linear regression model on BigQuery ML, city name variable as a key predictive component, data must be organized in columns, least amount of coding, maintaining the predictable variables.
The correct answer is option D, use Dataprep to transform the state column using a one-hot encoding method, and make each city a column with binary values.
Why is this correct? D. Dataprep provides a visual interface for data preparation. One-hot encoding properly transforms the categorical city variable into binary columns, fulfilling the requirements for column organization, minimal coding, and preserving predictability. Why are the others incorrect? A. Creating a vocabulary list and using TensorFlow involves significant custom coding, which contradicts the requirement of using the least amount of coding. B. Dropping the city column violates the explicit requirement to maintain the predictable variables, as the city name is a key predictive component. C. Assigning arbitrary numerical labels to nominal categorical data introduces unintended ordinal relationships in linear regression, negatively impacting the model's predictive accuracy.
You have been asked to build a model using a dataset that is stored in a medium-sized, 10 GB, BigQuery table. You need to quickly determine whether this data is suitable for model development. You want to create a one-time report that includes both informative visualizations of data distributions and more sophisticated statistical analyses to share with other ML engineers on your team. You require maximum flexibility to create your report. What should you do? The options are: Option A, use Vertex AI Workbench user-managed notebooks to generate the report. Option B, use the Google Data Studio to create the report. Option C, use the output from TensorFlow data validation on Dataflow to generate the report. Option D, use Dataprep to create the report.
To arrive at the correct answer, we focus on the keywords: medium-sized, 10 GB, BigQuery table, quickly determine whether this data is suitable for model development, informative visualizations of data distributions and more sophisticated statistical analyses, maximum flexibility.
The correct answer is option A, use Vertex AI Workbench user-managed notebooks to generate the report.
Why is this correct? A. Vertex AI Workbench user-managed notebooks provide maximum flexibility for exploratory data analysis, allowing the execution of custom scripts for both visualizations and sophisticated statistical analysis on a 10 GB dataset directly from BigQuery. Why are the others incorrect? B. Google Data Studio, Looker Studio, is excellent for general dashboards and visualizations but lacks the ability to easily perform sophisticated statistical analysis or run custom ML scripts with maximum flexibility. C. TensorFlow data validation on Dataflow is designed for large-scale, automated data validation pipelines in production, not for quickly creating one-time, highly flexible custom visualization reports. D. Data prep is primarily an interactive data preparation tool. While it provides basic data distribution visualizations, it lacks the maximum flexibility for sophisticated statistical analyses and custom reporting required here.
You have trained a text classification model in TensorFlow using AI platform. You want to use the trained model for batch predictions on text data stored in BigQuery while minimizing computational overhead. What should you do? The options are: Option A, export the model to BigQuery ML. Option B, deploy and version the model on AI platform. Option C, use Dataflow with the saved model to read the data from BigQuery. Option D, submit a batch prediction job on AI platform that points to the model location in cloud storage.
To arrive at the correct answer, we focus on the keywords: trained a text classification model in TensorFlow, batch predictions, text data stored in BigQuery, minimizing computational overhead.
The correct answer is option A, export the model to BigQuery ML.
Why is this correct? A. Exporting the TensorFlow model to BigQuery ML allows you to run batch predictions directly on the data where it resides. This eliminates the need to move large datasets out of BigQuery, significantly minimizing computational overhead. Why are the others incorrect? B. Deploying the model on AI platform is designed for online predictions, not large-scale batch processing, and does not minimize overhead for BigQuery data. C. Using Dataflow introduces additional computational overhead by requiring a separate processing pipeline and managing data extraction from BigQuery. D. Submitting a batch prediction job on AI platform requires exporting BigQuery data to cloud storage first, adding unnecessary data movement and overhead.
Refer to the attached Picture 1, reference exhibit. You are designing an architecture with a serverless ML system to enrich customer support tickets with informative metadata before they are routed to a support agent. You need a set of models to predict ticket priority, predict ticket resolution time, and perform sentiment analysis to help agents make strategic decisions when they process support requests. Tickets are not expected to have any domain-specific terms or jargon. The proposed architecture has the following flow. Which endpoints should the enrichment cloud functions call? The options are: Option A, 1 equals AI platform, 2 equals AI platform, 3 equals AutoML vision. Option B, 1 equals AI platform, 2 equals AI platform, 3 equals AutoML natural language. Option C, 1 equals AI platform, 2 equals AI platform, 3 equals Cloud Natural Language API. Option D, 1 equals Cloud Natural Language API, 2 equals AI Platform, 3 equals Cloud Vision API.
To arrive at the correct answer, we focus on the keywords: predict ticket priority, predict ticket resolution time, perform sentiment analysis, not expected to have any domain-specific terms or jargon.
The correct answer is option C, 1 equals AI platform, 2 equals AI platform, 3 equals Cloud Natural Language API.
Why is this correct? C. Endpoints 1 and 2 require hosting custom classification and regression models trained offline, achieved using AI platform. Endpoint 3 handles sentiment analysis for text without domain-specific jargon, making the pre-trained Cloud Natural Language API the most suitable choice. Why are the others incorrect? A. AutoML Vision is designed for analyzing images, making it entirely unsuitable for performing sentiment analysis on text-based support tickets. B. AutoML Natural Language trains custom text models. Since the tickets lack domain-specific jargon, training a custom model is unnecessary, and a pre-trained API should be used. D. Endpoint 1 requires a custom classification model hosted on AI platform, not a pre-trained text API. Furthermore, Cloud Vision API processes images, not text.
You have deployed multiple versions of an image classification model on AI platform. You want to monitor the performance of the model versions over time. How should you perform this comparison? The options are: Option A, compare the loss performance for each model on a held-out dataset. Option B, compare the loss performance for each model on the validation data. Option C, compare the receiver operating characteristic (ROC) curve for each model using the what-if tool. Option D, compare the mean average precision across the models using the continuous evaluation feature.
To arrive at the correct answer, we focus on the keywords: deployed multiple versions, image classification model, monitor the performance over time.
The correct answer is option D, compare the mean average precision across the models using the continuous evaluation feature.
Why is this correct? D. Continuous evaluation in AI platform automatically samples prediction input and output, letting you provide ground truth labels to monitor performance metrics like mean average precision over time. Why are the others incorrect? A. Evaluating loss on a held-out dataset provides a static assessment during model development, not continuous ongoing monitoring of deployed models over time and production. B. Validation data is strictly used during the training phase to tune hyperparameters, which does not address monitoring the performance of deployed models. C. The what-if tool is used for interactive visual exploration and bias analysis on static datasets, not for automated continuous monitoring of model performance over time.
You developed an ML model using Vertex AI and deployed it to a Vertex AI endpoint. You anticipate that the model will need to be retrained as new data becomes available. You have configured a Vertex AI model monitoring job. You need to monitor the model for feature attribution drift and establish continuous evaluation metrics. What should you do? The options are: Option A, set up alerts using cloud logging, and use the Vertex AI console to review feature attributions. Option B, set up alerts using cloud logging, and use Looker Studio to create a dashboard that visualizes feature attribution drift. Review the dashboard periodically. Option C, enable request-response logging for the Vertex AI endpoint, and set up alerts using pub/sub. Create a Cloud Run function to run TensorFlow data validation on your dataset. Option D, enable request-response logging for the Vertex AI endpoint, and set up alerts using cloud logging. Review the feature attributions in the Google Cloud Console when an alert is received.
To arrive at the correct answer, we focus on the keywords: Vertex AI endpoint, Vertex AI model monitoring job, monitor the model for feature attribution drift.
The correct answer is option D, enable request-response logging for the Vertex AI endpoint, and set up alerts using cloud logging. Review the feature attributions in the Google Cloud Console when an alert is received.
Why is this correct? D. Vertex AI model monitoring requires request-response logging on the endpoint to capture serving data for drift analysis. Alerts are sent to cloud logging, and the Google Cloud Console provides native visualization for reviewing feature attributions. Why are the others incorrect? A. Incorrect because it omits enabling request-response logging on the Vertex AI endpoint, which is a prerequisite for capturing the serving data needed to calculate feature attribution drift. B. Incorrect as it misses enabling request-response logging. Additionally, building a custom Looker Studio dashboard is unnecessary since the Vertex AI console provides native visualizations for feature attributions. C. Incorrect because using pub/sub and a custom Cloud Run function with TFDV is overly complex and unnecessary when Vertex AI model monitoring has built-in capabilities for drift detection.
You deployed a conversational application that uses a large language model, LLM. The application has 1,000 users. You collect user feedback about the verbosity and accuracy of the Model's responses. The user feedback indicates that the responses are factually correct, but users want different levels of verbosity depending on the type of question. You want the model to return responses that are more consistent with users' expectations, and you want to use a scalable solution. What should you do? The options are: Option A, implement a keyword-based routing layer. If the user's input contains the words detailed or description, return a verbose response. If the user's input contains the word fact, reprompt the language model to summarize the response and return a concise response. Option B. Ask users to provide examples of responses with the appropriate verbosity as a list of question and answer pairs. Use this dataset to perform supervised fine-tuning of the foundational model. Re-evaluate the verbosity of responses with the tuned model. Option C. Ask users to indicate all scenarios where they expect concise responses versus verbose responses. Modify the application's prompt to include these scenarios and their respective verbosity levels. Re-evaluate the verbosity of responses with updated prompts. Option D. Experiment with other proprietary and open-source LLMs. Perform A/B testing by setting each model as your application's default model. Choose a model based on the results.
To arrive at the correct answer, we focus on the keywords, different levels of verbosity depending on the type of question, scalable solution.
The correct answer is option A. Implement a keyword-based routing layer. If the user's input contains the words detailed or description, return a verbose response. If the user's input contains the word fact, reprompt the language model to summarize the response and return a concise response.
Why is this correct? A keyword-based routing layer provides a programmatic, highly scalable way to intercept requests and dynamically adjust prompts to deliver the appropriate verbosity based on question type. Why are the others incorrect? B. Supervised fine-tuning is resource-intensive and less effective for dynamically altering output verbosity on a per-query basis. C. Asking 1,000 users for scenarios and continuously modifying a monolithic prompt to include them all is not a scalable approach. D. A/B testing entirely different models does not address the core requirement of dynamically adjusting verbosity for varying question types.
You developed a Python module by using Keras to train a regression model. You developed two model architectures, linear regression and deep neural network, DNN, within the same module. You are using the training_method argument to select one of the two methods, and you are using the learning_rate and number_hidden_layers arguments in the DNN. You plan to use Vertex AI's hypertuning service with a budget to perform 100 trials. You want to identify the model architecture and hyperparameter values that minimize training loss and maximize model performance. What should you do? The options are: Option A, run one hypertuning job for 100 trials. Set number_hidden_layers as a conditional hyperparameter based on its parent hyperparameter training_method, and set learning_rate as a non-conditional hyperparameter. Option B, run two separate hypertuning jobs, a linear regression job for 50 trials, and a DNN job for 50 trials. Compare their final performance on a common validation set, and select the set of hyperparameters with the least training loss. Option C, run one hypertuning job with training_method as the hyperparameter for 50 trials. Select the architecture with the lowest training loss, and further hypertune it and its corresponding hyperparameters for 50 trials. Option D, run one hypertuning job for 100 trials. Set number_hidden_layers and learning_rate as conditional hyperparameters based on their parent hyperparameter training_method.
To arrive at the correct answer, we focus on the keywords, training_method argument to select one of the two methods, learning_rate and number_hidden_layers arguments in the DNN, hypertuning service with a budget to perform 100 trials.
The correct answer is option D, run one hypertuning job for 100 trials. Set number_hidden_layers and learning_rate as conditional hyperparameters based on their parent hyperparameter training_method.
Why is this correct? D. Conditional hyperparameters allow defining parameters active only for specific parent values. Since learning_rate and number_hidden_ layers apply solely to the DNN architecture, configuring them as conditional on training_method ensures Vertex AI explores the entire search space efficiently in one job. Why are the others incorrect? A. The scenario specifies that both learning_rate and number_hidden_ layers are arguments specific to the DNN. Therefore, learning_rate must also be a conditional hyperparameter, not a non-conditional one. B. Running two separate jobs prevents the Bayesian optimization algorithm from dynamically allocating the 100 trial budget across both architectures to find the global optimum. Why are the others incorrect? C. Manually splitting the tuning into two phases of 50 trials each is inefficient. Vertex AI's tuner is designed to simultaneously optimize categorical architectural choices and their associated conditional parameters.
You want to migrate a scikit-learn classifier model to TensorFlow. You plan to train the TensorFlow classifier model using the same training set that was used to train the scikit-learn model, and then compare the performances using a common test set. You want to use the Vertex AI Python SDK to manually log the evaluation metrics of each model and compare them based on their F1 scores and confusion matrices. How should you log the metrics? The options are: Option A, use the aplatform.log_classification_metrics function to log the F1 score, and use the aplatform.log_metrics function to log the confusion matrix. Option B, use the aplatform.log_classification_metrics function to log the F1 score and the confusion matrix. Option C, use the aplatform.log_metrics function to log the F1 score and the confusion matrix. Option D, use the aplatform.log_metrics function to log the F1 score, and use the aplatform.log_classification_metrics function to log the confusion matrix.
To arrive at the correct answer, we focus on the keywords: Vertex AI Python SDK, manually log the evaluation metrics, F1 scores, and confusion matrices.
The correct answer is option D, use the aplatform.log_metrics function to log the F1 score, and use the aplatform.log_classification_metrics function to log the confusion matrix.
Why is this correct? D. The aplatform.log_metrics function logs key-value scalar metrics like F1 scores, while aplatform.log_classification_metrics is specifically designed to log structured, complex classification metrics like confusion matrices and ROC curves. Why are the others incorrect? A. The log_classification_metrics function expects structured data and is inappropriate for scalar F1 scores, while log_metrics only accepts scalar key-value pairs, not confusion matrices. B. The log_classification_metrics function cannot log simple scalar metrics like F1 scores, which should instead be logged using the log_metrics function. C. The log_metrics function is meant exclusively for scalar key-value metrics and cannot be used to log structured classification metrics like a confusion matrix.
You are using Vertex AI to manage your ML models and datasets. You recently updated one of your models. You want to track and compare the new version with the previous one and incorporate dataset versioning. What should you do? The options are: Option A, use Vertex AI TensorBoard to visualize the training metrics of the new model version, and use Data Catalog to manage dataset versioning. Option B, use Vertex AI Model Monitoring to monitor the performance of the new model version, and use Vertex AI Training to manage dataset versioning. Option C, use Vertex AI Experiments to track and compare model artifacts and versions, and use Vertex ML Metadata to manage dataset versioning. Option D, use Vertex AI Experiments to track and compare model artifacts and versions, and use Vertex AI Managed Datasets to manage dataset versioning.
To arrive at the correct answer, we focus on the keywords: track and compare the new version with the previous one, incorporate dataset versioning.
The correct answer is option D. Use Vertex AI experiments to track and compare model artifacts and versions, and use Vertex AI managed datasets to manage dataset versioning.
Why is this correct? D. Vertex AI experiments is specifically designed to track and compare model iterations and metrics. Vertex AI managed datasets provide native support for creating and managing different versions of your datasets. Why are the others incorrect? A. Vertex AI TensorBoard visualizes metrics but isn't primarily for tracking model versions over time, and Data Catalog is for enterprise-wide data discovery, not Vertex AI dataset versioning. B. Model monitoring is used to detect training serving skew or data drift in deployed models, not to track versions. Vertex AI training doesn't handle dataset versioning. C. While Vertex ML metadata tracks ML artifact lineage, Vertex AI managed datasets are the recommended, native feature specifically for creating and managing dataset versions.
One of your models is trained using data provided by a third-party data broker. The data broker does not reliably notify you of formatting changes in the data. You want to make your model training pipeline more robust to issues like this. What should you do? The options are: Option A, use TensorFlow data validation to detect and flag schema anomalies. Option B, use TensorFlow transform to create a pre-processing component that will normalize data to the expected distribution and replace values that don't match the schema with 0. Option C, use tf.math to analyze the data, compute summary statistics, and flag statistical anomalies. Option D, use custom TensorFlow functions at the start of your model training to detect and flag known formatting errors.
To arrive at the correct answer, we focus on the keywords: third-party data broker, formatting changes in the data, model training pipeline more robust.
The correct answer is option A. Use TensorFlow data validation to detect and flag schema anomalies.
Why is this correct? A. TensorFlow data validation, TFDV, is explicitly designed for analyzing machine learning data, inferring schemas, and detecting data anomalies such as unexpected formatting changes before training begins. Why are the others incorrect? B. TensorFlow transform is intended for data pre-processing and feature engineering, not schema validation. Automatically replacing mismatched values with 0 hides underlying errors and degrades model quality. C. tf.math provides low-level mathematical operations. Using it to analyze data and flag anomalies requires building a complex custom solution from scratch, which is inefficient. D. Building custom TensorFlow functions to detect formatting errors adds unnecessary technical debt and maintenance overhead when a dedicated, robust tool like TFDV already exists.
You have built a model that is trained on data stored in Parquet files. You access the data through a Hive table hosted on Google Cloud. You pre-processed these data with PySpark and exported it as a CSV file into cloud storage. After pre-processing, you execute additional steps to train and evaluate your model. You want to parameterize this model training in Kubeflow pipelines. What should you do? The options are: Option A, remove the data transformation step from your pipeline. Option B, containerize the PySpark transformation step and add it to your pipeline. Option C, add a container op to your pipeline that spins a Dataproc cluster, runs a transformation, and then saves the transformed data in cloud storage. Option D, deploy Apache Spark at a separate node pool in a Google Kubernetes engine cluster. Add a container op to your pipeline that invokes a corresponding transformation job for this Spark instance.
To arrive at the correct answer, we focus on the keywords: pre-process these data with PySpark, Kubeflow pipelines.
Correct answer is option C. Add a container op to your pipeline that spins a Dataproc cluster, runs a transformation, and then saves the transformed data in cloud storage.
Why is this correct? C. Dataproc is the fully managed Google Cloud service for running Apache Spark. Using a container op to orchestrate a Dataproc cluster is the recommended best practice for running PySpark transformations within Kubeflow pipelines. Why are the others incorrect? A. Removing the data transformation step is incorrect because the PySpark pre-processing is a necessary step before training the model. B. Running heavy distributed PySpark workloads directly inside Kubeflow pods is an anti-pattern. A managed distributed processing service should be used. D. Manually deploying and managing Apache Spark on a GKE node pool introduces significant operational overhead compared to using a fully managed service like Dataproc.
You work for an online travel agency that also sells advertising placements on its website to other companies. You have been asked to predict the most relevant web banner that a user should see next. Security is important to your company. The model latency requirements are 300 ms at P99, the inventory is thousands of web banners, and your exploratory analysis has shown that navigation context is a good predictor. You want to implement the simplest solution. How should you configure the prediction pipeline? The options are: Option A, embed the client on the website, and then deploy the model on AI platform prediction. Option B, embed the client on the website, deploy the gateway on App Engine, and then deploy the model on AI platform prediction. Option C, embed the client on the website, deploy the gateway on App Engine, deploy the database on Cloud Bigtable for writing and for reading the user's navigation context, and then deploy the model on AI platform prediction. Option D, embed the client on the website, deploy the gateway on App Engine, deploy the database on memory store for writing and for reading the user's navigation context, and then deploy the model on Google Kubernetes Engine.
To arrive at the correct answer, we focus on the keywords. Security is important, 300 ms at P99, navigation context is a good predictor, simplest solution.
The correct answer is option C. Embed the client on the website, deploy the gateway on App Engine, deploy the database on Cloud Bigtable for writing and for reading the user's navigation context, and then deploy the model on AI platform prediction.
Why is this correct? C. App Engine provides a secure gateway, Cloud Bigtable offers low latency read/write access for navigation context, and AI platform prediction is the simplest, fully managed solution for model deployment. Why are the others incorrect? A. Directly calling AI platform prediction lacks a secure gateway, violating security requirements, and omits a database for retrieving navigation context. B. Although it includes a secure gateway, it lacks a database to store and retrieve the required user navigation context. D. Deploying on Google Kubernetes Engine introduces unnecessary operational complexity, directly violating the requirement to implement the simplest solution.
You need to quickly build and train a model to predict the sentiment of customer reviews with custom categories without writing code. You do not have enough data to train a model from scratch. The resulting model should have high predictive performance. Which service should you use? The options are: Option A, AutoML Natural Language. Option B, Cloud Natural Language API. Option C, AI Hub Pre-made Jupyter Notebooks. Option D, AI Platform Training Built-in Algorithms.
To arrive at the correct answer, we focus on the keywords, predict the sentiment, custom categories, without writing code, do not have enough data to train a model from scratch.
The correct answer is option A, AutoML Natural Language.
Why is this correct? A. AutoML Natural Language allows building high-performance custom text models, like sentiment analysis with custom categories, without writing code. It uses transfer learning, solving the issue of not having enough data to train from scratch. Why are the others incorrect? B. Cloud Natural Language API provides pre-trained sentiment analysis but cannot be trained on custom categories. C. Using AI Hub pre-made Jupyter Notebooks requires writing and executing code, which violates the requirement. D. AI platform training built-in algorithms require some coding for data preparation and job submission, and generally need more data as they train from scratch.
You work for a company that captures live video footage of checkout areas in their retail stores. You need to use the live video footage to build a model to detect the number of customers waiting for service in near real time. You want to implement a solution quickly and with minimal effort. How should you build the model? The options are: Option A, use the Vertex AI Vision Occupancy Analytics model. Option B, use the Vertex AI Vision Person/Vehicle Detector model. Option C, train an AutoML object detection model on an annotated dataset by using Vertex AutoML. Option D, train a Seek-to-Seek plus object detection model on an annotated dataset by using Vertex AutoML.
To arrive at the correct answer, we focus on the keywords: live video footage, detect the number of customers, near real time, quickly and with minimal effort.
The correct answer is option A, use the Vertex AI Vision Occupancy Analytics model.
Why is this correct? A. Vertex AI Vision Occupancy Analytics is a pre-built, ready-to-use model specifically designed to count people in designated zones from live video streams, perfectly meeting the requirement for quick implementation with minimal effort. Why are the others incorrect? B. While the person/vehicle detector identifies people, it lacks built-in zone counting and analytics features, requiring you to build custom logic to count waiting customers. C. Training a custom AutoML object detection model requires collecting and annotating a dataset, which significantly increases effort and time to deployment compared to using a pre-built model. D. Seek-to-Seek Plus is an architecture for sequence-to-sequence tasks, like text translation, not object detection, and building any custom model violates the requirement for minimal effort.